Hey, welcome back, Applied Pre-Cal. We're moving along in our linear functions unit. We're moving on today to properties of linear functions. This is a topic we're going to be coming back to over and over and over again, just because for this course, this is probably the big takeaway. If you can do this in grade 11, that's the main thing that we want you to get out of the course. Because it's so important, there are a lot of different names for what we're going to be looking at. So we'll start slowly today, and then as we take one more lessons, we'll add to that. So to start off, I want you to work with an example. And so here we have a table of values for degrees Celsius and degrees Fahrenheit. We have degrees Celsius from 0 to 20 in 5 degrees Celsius increments. And then we have their corresponding values for Fahrenheit. You might notice that there is a bit of a pattern going on with Fahrenheit. Now, it might be useful to also graph this information because that's what we've been working with so far. All right, and there we are. When we graph it, we can see that there is, in fact, a linear relationship when comparing Celsius to degrees Fahrenheit. That linear relationship, based on our information, whether you're looking at our table of values or you're looking at the graph, is that for every 5 degrees Celsius, we are changing by 9 degrees Fahrenheit. So every 5 degree increase in Celsius, we're increasing by what appears to be 9 degrees Fahrenheit. Okay, so that's reasonable. We can figure that part out, and it's nothing new that we haven't worked with already. What can I add into this? Like, where does the properties or functions come into? And one simple question will get us started on figuring that out. And that question is, what is the rate of change? Well, what does the rate of change mean? Maybe that's a good starting point. So let's get a definition down. So the rate of change, that's going to describe how much our dependent variable is going to be influenced for every change to our independent variable. If you recall, our independent variable is something that changes automatically. It's independent of anything around it. The dependent variable is going to depend on what that independent variable changes to. On our graph, recall that our independent variable is on the x-axis, always. Our dependent variable will be on our y-axis, always. And with that information, we can then come up with some sort of equation to help us solve for the rate of change. So the rate of change, what we use to denote it is a little triangle. And the formula is simply the rate of change, so delta, which is a triangle, is equal to y2 minus y1 divided by x2 minus x1. When you first see it, it looks like there's a lot going on. There's like those little 2's and little 1's there. There's a triangle for some reason. It's actually a lot easier to work with than it might seem on the surface. The 2's and the 1's are just labels. So whatever point I choose for y2, for example, if I chose 41 degrees Fahrenheit for y2, I have to choose a corresponding x coordinate for x2. So if I chose 41 for y2, I have to choose 5 for x2. So let's calculate a rate of change. Okay, so to solve this, I've just chosen the first 2 points that I've seen. So I'm using x2 and y2 for the second point, and x1 and y1 for my first point. One thing to keep in mind is it seems counterintuitive that the y goes on top. So I know x comes first in the alphabet, well, x goes on the bottom in this case. And so when we do our calculation, it ends up being 41 degrees Fahrenheit minus 32 degrees Fahrenheit. That leaves us with 9 degrees Fahrenheit over 5 degrees Celsius minus 0 degrees Celsius, which leaves us with 5 degrees Celsius. Don't forget your units in the final answer. I'm going to ding everyone on that if you do. The units are critical when dealing with the rate of change. Otherwise, you're not solving anything. Okay, so don't forget your units. We end up getting a rate of change of 9 degrees Fahrenheit for every 5 degrees Celsius. And if you wanted to punch in your calculator, you might do 9 divided by 5. You end up getting 1.8 degrees Fahrenheit per degree Celsius. So every degree Celsius, whenever that change is going up or down, our degrees Fahrenheit are going to be changing by 1.8. Here's a question I'm hoping some of you might be making the connection. But why did I choose the first 2 points? What would happen if instead I chose, I don't know, the first and the last point, or the last 2 points? Well, let me show you. One example that I've chosen for my x and my y2 I've gone with the second point again. For my x and y1, I've actually gone for the last point. So the calculation is here. I end up doing 41 minus 68, 41, y2 minus y1, and 5 minus 20, x2 minus x1. I end up getting negative 27 degrees Fahrenheit over negative 15 degrees Celsius. But if you use the greatest common factor, in this case it's 3, we can divide both numbers by 3. You can actually divide them both by negative 3. You end up getting the exact same relationship. And this is only true because we have a linear relationship. In fact, we have a linear function, which makes this true. If you did not have a linear function or a linear relationship, you could not calculate the rate of change for the entire picture. You could only calculate it between 2 points. Okay, but what does that really do for us, right? Like, we calculate the rate of change, we could probably do it just by looking at the graph. And yeah, you could. Some people can do that. Sometimes you got to do the actual calculation for it. But I want to show you why the rate of change is so valuable. Let's write down the formula to convert Celsius to Fahrenheit. So the formula, I'm going to let F be my degrees Fahrenheit. I'm going to let C be my degrees Celsius. This is from page 273, actually. You did a problem on this. But the formula is Fahrenheit, degrees Fahrenheit is equal to 9/5 times C plus 32. What do you notice about the numbers in the equation here? And if you recognize that our rate of change is directly in our linear equation, our linear relationship. In fact, there's something else that you might notice, and maybe not. The other number in this equation is 32. If I appear over here for a moment, where do you see 32 on your graph? These are properties of linear functions. When you have an equation of the form y equals mx plus b, where y is your y variable, x is your x variable, m will always be your rate of change. And b will always be your y-intercept. The y-intercept, if you recall, is the point where your line will cross the y-axis. So anytime you have an equation of the form y equals mx plus b, and y can be any letter as long as it represents your y-axis, and x can be any letter as long as it represents your x-axis, then whatever value is attached to x will be your rate of change, and whatever value is by itself will be your y-intercept. All right, so that's today's lesson. I'm hoping you're starting to connect the dots with this applied pre-calc course, in particular with the rate of change and the value of having these linear expressions. We'll have one more lesson, and that'll be working more with graphs, so going from the graph to the equation. And then after that, I'll have another one of those online assessments available for you. It'll be just like your last one where you can fill it out online and upload some pictures. Yeah, well, I'll give you some more information on that a little bit later on. Maybe I'll make a separate video for that. But you have a lot of practice for this unit. Get started on that, and absolutely let me know if you have any questions. We'll take it from there.